Okay, so in the last video, we started to talk about simple harmonic motion. And basically, simple harmonic motion occurs whenever the acceleration of an object is proportional to the displacement of the object, but in the opposite direction, which is a definition that you should have in your notes. And last class, we were taking a look at a specific example of simple harmonic motion, which is when you have a mass attached to a spring oscillating on a frictionless horizontal surface. And so I worked out using Newton's second law. Last class, I showed how you can use Newton's second law to get to the simple harmonic motion equation. And so just really quickly, I want to recap the fundamental equations that you must have for simple harmonic motion. Okay, so from a mathematical perspective, in order for an object to oscillate in simple harmonic motion, the acceleration of the object has to be equal to some constant times the displacement. Okay, this is what it means to be proportional. Okay, so one of the conditions is that the acceleration must be proportional to the displacement from equilibrium. And then the other condition is that it must be acting in the opposite direction. Okay, and so that's what this little negative sign represents. Okay, now the number that goes here in front of the x is called omega squared, and omega is what we call angular frequency. And I think we talked a little bit about this last class, but this is just a recap. Okay, and so just to say a few things about angular frequency. Angular frequency is obviously it has a symbol omega, which we've seen before when we did circular motion. And it's actually kind of related to angular velocity, which is the last time we saw omega. Angular frequency is 2 pi divided by the period of oscillation, or you could also write that as 2 pi times f, where f is the frequency in hertz. Okay, and so angular frequency basically has to do with how quickly is the oscillation happening. Okay, and so everything I'm writing right now is true for any type of simple harmonic motion. Now, last class we were taking a look at a specific example of simple harmonic motion, which is for a mass on a spring. Okay, and so for a mass spring system, um, and I'm not going to go through all of this again, but for a mass spring system, the equation we ended up getting was we got the acceleration is equal to negative kx divided by m, which if you compare to this equation, which again, this is the fundamental equation needed for simple harmonic motion, we can see that this satisfies the condition for simple harmonic motion as long as this k over m thing is equal to omega squared. Okay. In other words, omega, the angular frequency, is equal to the square root of k divided by m. And if you take this and plug it into the equation for period, then you can show that the period of a mass attached to a spring is equal to 2 pi times the square root of L over G. Okay, I'm sorry, let me erase that. It's equal to 2 pi times the square root of m over k. A little bit of a mistake there, sorry. And again, so this is the equation that lets you calculate the period of a mass on a spring. As we'll see here later today, there's a similar equation to calculate the mass, to calculate the period of a pendulum. And really, any type of simple harmonic motion that occurs in nature is going to have a similar looking equation for period. And I will show you later how the equation for the period of a pendulum comes about. But basically, what it comes down to is being able to write down Newton's second law, or a version of Newton's second law, and get it into some type of equation that looks something like this. And then whatever constant is in front of the x is equal to omega squared, and then you just go from there. Okay, and so that's basically how that works. Okay, and so when we take a look at the pendulum later, keep in mind that in order to prove that it's simple harmonic motion, we want to basically use Newton's second law to get it into this form. Okay, but we'll come back to that later. So make sure you have all these fundamental equations down. I think most of this we talked about last class, but in case you miss anything, make sure you have everything added to your notes. And also make sure that you understand that some of these equations are specifically for a mass on a spring. Okay, so everything I'm drawing a box around now, okay, this is for the specific case of a mass on a spring, and that is an example of simple harmonic motion. Everything which I will do a red box around now, okay, is true for any type of simple harmonic motion, no matter what the situation is. Okay, and so make sure you distinguish between the general aspects of simple harmonic motion and the specific examples of simple harmonic motion. And so as far as specific examples go, we're only going to look at two. One is going to be the mass on the spring, and the other is going to be a simple pendulum. Okay, so make sure you have that down in your notes, and let's go to the next slide. Okay, so erase this. So this is kind of where we left off last class, is looking at the equations for simple harmonic motion. Okay, and I think we got to the point in the notes where we had the first equation, which is the position as a function of time, but I don't think we got past that. And so without proof, I will write down the equations for motion, which are true for any object moving in any type of simple harmonic motion. And we kind of saw a demonstration of this in the Walter Lewin video that we watched last class with the paint can attached to a spring. Okay, and so the first equation we have is we have x of t is equal to a times cosine omega t plus this letter right here, which I will call phi. That is a Greek letter. And basically, I'll tell you what everything represents. But before I do that, I will tell you the equation of motion that is on the formula sheet looks a little bit different than this. And so what I'm writing down for you now is kind of the most general way that these equations are written. The way it's on the formula sheet is a little bit different, and you'll be able to see the difference in a few minutes. But I just want you to see the most general form, just so you kind of understand the bigger picture of everything. Okay, so in this equation, A is going to be the amplitude of the oscillation. Hopefully you're familiar with the concept of amplitude from pre-cal. If not, you should already have the definition of amplitude in your notes. Omega, of course, is our wonderful angular frequency. Remember, that is equal to 2 pi times the normal frequency. T, of course, is time, and this right here is a Greek letter phi. This represents what's called the phase angle or the phase shift, is what you call it in pre-cal, and that basically represents the horizontal shift of the function. Now, in all the examples I've seen so far in the homework, this value is always equal to 0, but just to be safe, I thought I would include it in the equation. If it doesn't say anything in the problem about a phase shift, then you can usually assume that value is equal to 0. Okay, so this is where we left off last class with the equation for x of t. So what about the other equations? Okay, so the equation for v of t is equal to negative a times omega times sine of omega t plus phi. Okay, and you'll see these two equations are kind of similar to each other, but because one is a cosine and one is a sine, they're separated by an angle of um, 90 degrees, and so they're kind of offset from each other. The other thing I want to point out, just like from a mathematics standpoint, is sine and cosine. The range of sine and cosine is between -1 and 1. In other words, this value right here, the sine omega t plus phi, that number can never be greater than 1. And what that means is, if we want to think of what is the maximum value of v, in other words, what is the maximum speed that this object can have in simple harmonic motion, that's going to be this coefficient out in front of the sine, because the sine function can never be a number bigger than 1. So whatever is in front of the sine basically serves as the maximum value of the function, which in this case is going to be v max. Okay, so in other words, you can calculate v max just by doing a times omega, assuming that you have the amplitude and assuming you have the angular frequency. Okay, and of course, in case it's not obvious, I do want to point out that both x of t and v of t, these are not constant. Obviously, they both change as a function of time. Okay, now the last one that I want to show you is the acceleration equation. Let me just write this slightly smaller. This is v max. And so a of t is equal to negative a times omega squared times cosine omega t plus phi. Okay, and if you compare x of t with A of t, you'll see these two equations are the exact same. The only difference between the A of t equation and the x of t equation is that there's a minus sign, and in front of the cosine there is an omega squared. But besides that, they are the exact same equation, which means that A is equal to negative omega squared times x, which is our definition of simple harmonic motion that we talked about on the last slide. Okay, so in other words, everything works out, right? So if these are the equations of motion, they are consistent with what I told you the definition of simple harmonic motion is at the beginning of the video. That is, the acceleration has to be proportional to the displacement and in the opposite direction of the displacement. Okay, so these are our equations of motion. All right, so pause it there. Make sure you have all this down. Let's go to the next slide. Okay, and if you're a visual person, these are just kind of what the graphs would look like. Between x of t, v of t, and a of t for an object in simple harmonic motion. I do want to point out that if an object starts at a maximum value, okay, that means it starts at its amplitude value. Okay, at that point, at the endpoints, the velocity is equal to 0. And so this object is going to move from the highest position, which here the amplitude is 1, down to -1. Okay, so this is the other endpoint, and at the other endpoint, the velocity is also equal to 0. Okay, so in other words, every time the position is at one of the endpoints, the velocity is equal to 0. And the reason for that is just because at the endpoints, the object, if you imagine the mass of the spring, as a concrete example, every time it reaches one of the endpoints, it has to stop, change directions, and go back in the opposite direction. Okay, and so these graphs should be consistent with everything we've talked about in the past. Okay, so pause it there if you want to jot those down or sketch those graphs. Okay, so just to show you the equations actually on the formula sheet, here they are. The top equation is really just for the specific example of the mass of the spring that you see here. This sentence here, it says x of t and v of t are the same as if the mass is traveling around a circle of radius a with velocity v max equals 2 pi a over t. Remember, capital T is the symbol for period, which is equal to omega times a. So in other words, they're telling you that v max is equal to a times omega, which we talked about on the last slide. If you take a look at this equation, this looks very similar to the equation we saw for x on the last slide. The only difference is that instead of having omega times t, they have 2 pi divided by the period. But of course, omega is equal to 2 pi divided by the period. So this equation right here is the same equation we saw previously. The only difference is that there's no phase shift. And so I think the fact that they don't put it on the formula sheet is probably an indication that you're not going to have to worry about phase shift, hopefully. And of course, here you see the equation for V. They don't have a minus sign, which is just a mistake on their part. There should be a minus sign there to be completely correct. But here you can see that they don't give you the equation for the acceleration. The equation for the acceleration is, of course, equal to, the acceleration is minus omega squared times x, which is what we talked about before. Okay, I also want to point out right here, this that I'm drawing a box around right now is always true for any type of simple harmonic motion. This part of the equation is only for a mass on a spring oscillation. Okay, so it's always true that the angular frequency is equal to 2 pi times f, or 2 pi divided by the period. But the square root of k over m is only for this one specific example of simple harmonic motion. Okay, so just to remind you, there's many, many, many different types of simple harmonic motion in the universe. Okay, anything with an m over k that is specific for this one instance of simple harmonic motion where something is attached to a spring as is oscillating on the spring. Okay, so just make sure that's clear. Okay, so let's go to the next page. And go ahead and just add these to your notes. I think most everything on here is pretty self-explanatory. You want to really focus here on these bullet points here. And then, of course, these as well. Okay, so basically everything with a box around it is important for you to know. So pause it there and make sure you add that to your notes. And the part about kinetic energy and potential energy is also helpful because in simple harmonic motion, by by definition, energy is always conserved. And so anytime you have a problem with simple harmonic motion, you can also apply conservation of energy to that problem in order to help you answer questions. Okay, so something to keep in mind. Make sure your calculator is in radian mode if you're using trig functions in this unit. Okay, so pause there. I'm going to go to the next slide. Okay, so there are some examples in the notes. I'm going to skip the examples for now and talk about those in a separate video. Um, what I want to do now is I want to talk about something that pertains to your lab, but I want to derive the period of oscillation for a simple pendulum. Okay, and so in other words, I'm going to show you basically where the equation comes from that lets you calculate the period of oscillation for a simple pendulum. So I said at the beginning of the video, we're going to look at two examples of simple harmonic motion. One is the mass on the spring, okay, which we talked about before. And so now we're going to see a simple pendulum, and this is kind of going to be the basis of your lab that you're doing next class. Okay, and so give me just a second. Okay, so let me kind of show you how this works, and there's a few different ways to do this, but I'm going to do what I think is the easiest way. So imagine we have a string attached to the ceiling, and at the end of the string, there is a mass, okay, and the value of the mass is m. And let's say the length of the string is L. And let's say I pull the string back and I let it go and I pull it back to here where the angle here is theta. Okay, and I let it go. And of course, we all know what's going to happen. It's basically, it's going to swing back and forth. And so this is what's called a pendulum. Okay, this is called a simple pendulum. You can imagine like a child on a swing, or like somebody trying to hypnotize somebody else, and they have the watch or whatever attached to string, and it's going back and forth. That is what a pendulum looks like. Okay, and so what I'm going to do for you now is I'm basically going to justify the fact that this is simple harmonic motion, although it's not really simple harmonic motion, as we'll see here in a second. And the way I'm going to do that is I'm going to use Newton's second law for rotational motion. Okay, which means I'm going to use torque. And so let's start with a free body diagram. Okay, so the forces in this situation, I have force of gravity and I have tension. And of course, excuse the bad drawing. And so let's think about torque. We know from, 2 units ago that Newton's second law for rotational motion says that the net torque on an object is equal to the moment of inertia times the angular acceleration. And so what is the net torque in this situation? Well, there's two forces here, but the torque from tension is actually equal to 0. And the reason is if you look at the tension vector is pointing towards the pivot point. But remember, torque is equal to RF sine theta. And in this situation, the R vector points from the pivot point to the mass. And so the angle between the R vector and the F vector for tension is 180 degrees. And sine of 180 is 0, meaning that the tension in the situation does no torque. Now the torque from the force of gravity would be equal to R, which here the value of R is L, times the force, and of course the force of gravity is mg, times the sine of the angle, which is sine theta. Okay, and normally you would write it as mgl sine theta. Of course, the order doesn't actually matter, but it just looks nicer. And so there's only one force providing a torque in this situation. And so if I plug this in for the net torque, right, the net torque would be the sum of the torques, but there's only the one torque, then I have mgl sine theta on the left side. I, remember, is moment of inertia, but the moment of inertia for a point mass is equal to mr squared. Okay, but here the value of r is the same as the length of the string, and so that would be ml squared. And then I have alpha. Okay, Now, if you look here, you'll see the mass cancels and one of the lengths cancel. And we have an equation that we end up with. Oh, I'm so sorry. I forgot a minus sign. This torque has a minus sign in here because the force of gravity in the situation is trying to decrease the angle. And so this is actually a negative torque. Okay, and so I end up with alpha equals, let's see, um, negative g divided by L times sine theta. Okay, now this is not an equation for simple harmonic motion. And so um, a simple pendulum is not actually an example of simple harmonic motion, which I realize that it's funny since I'm supposed to be doing examples of simple harmonic motion, and I did all of this work, even though the end result is that a simple pendulum is actually not simple harmonic motion, because in order for this to be simple harmonic motion, the acceleration has to be proportional to the displacement. There's no displacement in here because remember theta is the angular displacement, but this is not theta, this is sine theta. Okay, so why am I talking about this in a video about simple harmonic motion if it's not actually simple harmonic motion? Well, there's something in math called the small angle approximation. Okay, and the small angle approximation, if you get a calculator and put it in radian mode, you can test this for yourself. But the small angle approximation says that if the angle is small, and when I say is small, small is kind of like a subjective term. In fact, one of the things you're going to be doing in your lab next class is you're going to be investigating like how small is small enough. So let's just say if the angle is pretty small, then it's mathematically true that sine theta is very, very close to theta. Okay, and if you don't believe that, you can get a calculator and just make up some numbers and plug it in. For example, if you do like sine of 0.1, you'll see sine of 0.1 is a number that's actually very close to 0.1. Okay, so the smaller the angle, the closer sine theta is to theta. But if the small angle approximation holds, then in this equation, I can actually replace sine theta with theta. And then here I have the equation for simple harmonic motion. Because remember at the beginning of the video, I talked about in order to have simple harmonic motion, I have to have the acceleration, which I have here, is equal to some constant with a minus sign in front of it times the displacement, which I have here. Okay, and so in this equation, based off of what I talked about before, remember the number in front of the displacement is omega squared. So here omega squared would be g divided by L. Okay, whereas before for the mass on the spring, omega squared was equal to k divided by m. For a simple pendulum, the equation comes out different because the math works out different. Okay, and so what you can show is because omega is equal to 2 pi divided by the period, okay, if you take this and you plug it into this equation, okay, you can show that the period for a pendulum is equal to 2 pi times the square root of L divided by G, where L is the length of the string and G is the acceleration due to gravity. Okay, and so this equation allows you to calculate the period of a simple pendulum. And so one of the things you'll be doing in your lab is basically you'll be testing the period of an object oscillating as a pendulum at different angles. And one of the things you'll be looking for is if you make the angle bigger, is it still match the equation that you see here? Okay, so this ties directly into your lab that you'll see next class. Okay, so pause it there, rewind. If there's anything you don't understand, rewind and go through everything again. Make sure you get everything down in your notes because I do want you to understand all of this. Okay, I do want you to understand the two different situations of simple harmonic motion that we've seen so far. One is the mass on the spring. One is the simple pendulum that we just saw. Okay, but I want you to understand the deeper concept, which is that you get simple harmonic motion anytime you can somehow get the acceleration equal to a constant times the displacement with a negative sign in front. Anytime you get that situation, it's going to be simple harmonic motion. Okay, and I've given you two examples here, but there's countless others that I could show you if we had more time. But unfortunately, we are out of time. I'm going to make a video going through several different examples from the notes. But hopefully this video, along with the examples video, will give you all of the information you need for your lab next class. The next step after this is we're going to move on in the notes and talk about waves. Okay, so please rewatch this video if there's anything you miss. If you have any questions, please email them to me or please ask them in tutorials. Okay, and I will see you guys in the next video.